Is this equation all right with everybody? Okay. Now I'm going to multiply through by each of the minus I phi 1. So I will get r dot plus I phi 1 dot r equals mu minus br squared minus c2r squared r plus ar squared e to the I phi 1 plus phi 2 plus phi 3. And so I see that I have, okay, so I separate this now, I separate it into two equations, as I usually do the real part and the imaginary part of r dot equals mu minus br squared minus c2r squared r. And now I have plus ar squared cosine the sum. And for the other equation, I have phi 1 dot equals, times r, is equal to ar squared sine phi. Oh, but it's minus because, hold on, what did I do? I needed to multiply through by minus e. So I have minus here. This is a minus, so this is a minus ar squared sine phi. Okay, everybody agree with this? So now, if I'm looking for steady states, there are two possibilities. Okay, first of all, I see this, if I want this to be 0, I better have sine phi being 0. I'm looking for steady states. I'm looking for steady hexagonal states. Sine phi can be 0 in two ways. It could be, you could have phi equals 0 or you could have phi equal pi. Right? And that's going to influence whether you put plus or minus 1 here. So we get that, we get the two possibilities, phi equals 0 or phi equals pi. And both of those will now make phi dot equals 0, so that part's okay. But here we have r dot equals mu minus br squared minus c2r squared plus ar squared. And here we have r dot equals mu minus br squared minus c2r squared minus ar squared. And that's going to make a difference. And this is a quadratic equation. You can solve it. It's not pretty, but it's not worse than other quadratic equations. You have, excuse me, this is a quadratic equation, so it has two solutions, and this is a quadratic equation, so you have two solutions. So you have 4 solutions altogether. And the way it turns out is that, as I said, they are different. If you have the phi equals 0, then the picture, the hexagonal picture, ends up looking like this. And if it's phi equals pi, it looks like that. Now, what is this and that? Here, whenever all three meet, you have, okay, I'm sorry, I should say what all these things are. These lines are lines of positive and negative oscillation of e to the ikx. Okay? So you have 0, you have plus 1, minus 1, plus 1, minus 1, plus 1, minus 1, plus 1, minus 1. That's what a plane wave is going to look like. Plus 1, minus 1, plus 1, minus 1. Okay? And that is being drawn, say, for the one that goes in, the one that has a wave vector like this. We have plus, minus, plus. Okay? So plus, minus, plus, minus, plus. I've just drawn the maxima and the minima of the one that goes in this direction. And you can see how it works for the other ones. I have plus, minus, plus, minus, plus here for this one. And then I have the remaining one that's plus, minus, plus, minus, plus. Now I hope I'm right about this. Yes, whenever three curves meet here, 2 of them are negative and 1 of them is positive. And whenever 3 meet here, 2 are positive and 1 is negative. And sometimes you have 3 negatives, and here sometimes you have 3 positives. So there really are 2 different possibilities. Okay, is that true what I said? I think it's true. Here you have 3 positives all meeting. Here you have 3 negatives all meeting. And I'm going to claim that, and here you have 2 positives and 1 negative, and here you have 2 negatives and 1 positive, and I'm going to claim that that's what you have all along. That in this setup, you never have 3 negatives meeting, and in this setup, you never have 3 positives meeting. Okay? Hence, they're named down hexagons here and up hexagons there. And so we have a bifurcation, yes, to hexagons, but 2 different kinds of hexagons. And generally, when we have a bifurcation with branches that are different from one another, okay, there were several possibilities that we saw about steady bifurcations. We saw that there were pitchforks, and there were multiple solutions, yes, but they were equivalent. Maybe they were equivalent that they were up and down, left and right or whatever, or they were circle pitchforks, which we've drawn somewhere there, and they were all equivalent too. We had saddle node bifurcation, and those are 2 inequivalent branches, but the way they arise is there's nothing on one side, and then they're spontaneously created here. So this was the pitchfork, and this was the saddle node. And those are the main ones that you see. But there was a third one that was mentioned, which was transcritical. And in transcritical, you have different branches, but they have different properties, unlike this. And it turns out that's what bifurcations to hexagons look like. They are transcritical, and this is due to their symmetry properties, just all described there. The presence of that quadratic term, it all goes together. You can have a quadratic term because K1 plus K2 plus K3 adds up to 0, and hence e to the I is 1. Hence, you can put Z2, you can have a quadratic term, you can put Z2, Z3 bar into the Z1 equation. And when you have a you remember that the normal form, you might think we're awfully far removed from these one-dimensional things that we were doing before, where we had x dot equals mu minus x minus x cubed, and I said there were only linear and cubic terms, and here it was x dot equals mu minus x squared. This was not a situation where you always have a 0 solution, and that is the one we've just been looking at. And in this one, we had x dot equals mu x minus x squared. We had a quadratic term. And this same, again, it looks as if the calculations are very different, but the fact that we have quadratic terms in these cubic equations is what gives you the transcritical bifurcation. You'll recall also that this is the basic transcritical bifurcation, but we said that physicists don't like things to go away to infinity, so we generally add another branch like that. And we say that it looks kind of like a pitchfork, but it is, but where the 2 branches are different, and where there's an interval over which before it turns around. And that is just what it looks like for hexagons. Here, if we go here, go to the bifurcation diagram, this is what it looks like. Rolls are pitchforks. Necessarily they're pitchforks. We've been discussing that. We've said it's a circle pitchfork. You can have any phase. Symmetry tells you that it's a circle pitchfork. Okay. And that is the case. This is the trivial branch. You're bifurcating from nothing. Okay, I should maybe have gone back and said an obvious solution to these set of equations is z equals 0. We assume that we're bifurcating from homogeneous state. So we didn't go through all the arithmetic, but we could have searched for solutions that only had Z1 and had no Z2 and Z3. We could see what would happen then. Everything here would disappear. This would disappear, and we would just have the circle pitchfork here. Right? We would have Z1 dot equals mu minus B Z1 squared times Z1, the circle pitchfork. We also have circle pitchfork in the Z2 direction, and also in the Z3 direction. You might think, why just 3? This is supposed to be an infinite featureless layer. Yes, but we have put down a grid, by a hexagonal grid, we have forced it to be hexagonal this way. We have not allowed there to be roll solutions that are in some arbitrary direction. We have written everything in this form. We have selected a specific direction, say the K1 direction, from which K2 and K3 follow. We have selected a hexagonal lattice. We have looked for things that where we could translate Z1 as Z2 and Z3 according to those wave vectors. We have forced it to be hexagonal. This is not a result. This is part of our construction. But out of the construction comes the following results. The results that you have rolls of all 3 kinds. Our construction led to these equations here. And now we can examine the solutions of these equations. One of them is rolls. So 3 of them are rolls, or 6, more than that. Each one is a circle pitchfork, so 3 infinities worth of rolls in 3 different directions. We have 2 kinds of hexagons, the up and down hexagons, and then we have a situation we did not look at. We can do that. Can be a homework problem where you have 2 of them. Okay, we looked at all of them being equal. That's hexagons. We looked at one of them being finite and the other 2 being 0. We could look at a situation in which 2 of them are equal and another one is a different value, and that's rectangles. You can imagine if you have this and this being equal, then this is going to form, it forms rectangular patterns, and indeed that's what you get. And they bifurcate from, but they're not created from 0, they bifurcate between rolls and hexagons. Let's say at this point, well, anyway, we'll just say that there. These 2 branches of up and down hexagons, remember I said we had two quadratic equations and hence 4 solutions? So the way that works with the arithmetic is merely like this here. We end up with the solutions to these, once you set these to be 0, are a curve like this, and another one like this. Okay, that's these 2. 2 solutions to this and 2 solutions to this. 2 to this and 2 to that. Okay, but these are equations for R, which is supposed to be positive. We absorb negativity in the phi, so we erase this part here because R isn't supposed to be negative, and that's how you get this picture here. And it bends back and then forth. And that is actually true. I mean, in physical situations where you have hexagons, which you do in Marangoni convection, and in fact, I can mention an interesting story here. Baynard, of course, observed convection, then Rayleigh explained it. And Rayleigh explained with the theory that we mentioned in the very first time, with the pressure of what you have is the light fluid and the heavy fluid, and the light fluid is in an environment where the gravity is low, but so is the grad P, and they are compensating one another, right? Remember that? And then in the cold area here, the fluid is dense, so the gravity is high, but so is the grad P, and they're compensating one another. And then you switch where the 2 particles are, right? And they find themselves in the wrong environment and all that stuff. Okay. So that is Rayleigh's explanation, and then he followed that up by calculations for how it happens. But in fact, much later in the 1960s, it was discovered that what you should see in Rayleigh-Baynard convection is rolls. But because, let's see if I can get this right, just as we saw in Swift-Hohenberg, it's because there are no quadratic terms. If you manipulate the Boussinesq equations and you project the right way and so on, you end up with no quadratic terms. Now some of you are going to say, wait a minute, there's quadratic terms in Navier-Stokes, u dot grad u dot grad t, that's quadratic. But if you project onto the eigenvector, that goes away, and there is some sense, which I'm certainly not prepared to say now, in which there aren't quadratic terms. We know that when there are no quadratic terms, we get rolls. When there are quadratic terms, we get hexagons, and we saw why that was. This is all very, it's strange to think that it works. It's such simple reasoning, but this thing about how phi1 plus phi2 plus phi3 is 0, and hence you're allowed to have the term z2, z3 bar in that equation for z1. That's very deep. Anyway, my point is that Bénard, what he saw and described were hexagons. So this is actually not compatible with Rayleigh's explanation. When you do the equations correctly, Rayleigh's equations and Rayleigh-Bénard equations, you do not get something that's equivalent. I mean, of course, these things here are not the Boussinesq equations. They're not, but take my word for it, although I cannot do it. You can take the Navier-Stokes, the Boussinesq equations, and do all kinds of stuff to them, and they come down to equations like this. I say I don't know how to do it, but there's generations of people who did that kind of stuff before computers. Bénard saw hexagons. Hence, in the equations that were governing what he was doing, there were quadratic terms, because hexagons cannot be produced without quadratic terms. Hence, Rayleigh's explanation did not apply to Bénard's experiment. And then that was someone named Rosenhead. That was in around 1965. So from 1918 or 1920 or 1912 or sometime like that until 1965 or something like that, people thought that Rayleigh had explained Bénard's experiments, but he had not. Rayleigh had explained something which is now called Rayleigh-Bénard convection, although it should not be, because that's not what Bénard observed. What Bénard observed is something called Bénard-Marangoni convection. And that has to do with the surface tension. It has to do with the fact that surface tension varies with temperature. And again, I'm not equipped to tell you why that leads to quadratic terms, although you can think, perhaps in part, but I don't even know if that's the explanation, the fact that this free surface is different from, there's asymmetry there because you have free surface and on the bottom you have a plate. But I'm not sure that's what leads to it. Might be, but okay, I don't know. I better not get into trouble here. Anyway, Marangoni convection does have quadratic terms in it, and so does typically lead to hexagons, nothing forbid, and that is what Bénard saw. But that was only realized much later. And they didn't drop the term Bénard from Rayleigh-Bénard convection. They kept it in to be nice and to him. Okay, so that is so this is how mathematicians or how hydrodynamicists or whoever it is who whatever label you want to attach to people analyze the square and the hexagonal patterns as superpositions of rows like this versus rows like this, this, and this. Okay, and you can do it right. There's volumes written on it, and you can do it in the proper way. You already saw in the Faraday problem. Although maybe I'm going to mix up what I showed in my seminar yesterday and what I showed in the class, square and hex. Maybe I didn't show this. Let's see. In the Faraday problem, which is the shaken layer, you can actually see both hexagonal patterns and you can see these are hexagonal. You see this is surrounded by 6 little hills, right? Or you can see square patterns where each hill is surrounded by 4 other, each hollow is surrounded by 4 hills. Now, in experiments, these spontaneously appear. If you oscillate the layer of fluid at a fairly low amplitude, you will get squares, and if you oscillate at a higher amplitude, you will get hexagons. And I believe, at least the last time I asked the people who know how to do this, that nobody really knows when you go from squares to hexagons. This transition has not been analyzed. You saw for yourselves that the frameworks in which we talked about squares was making a square grid, and we talked about a framework in which we made a hexagonal grid. We did not make a framework in which we could talk about both patterns and how they compete, and when squares could become unstable to hexagons. We didn't talk about that, and to the best of my knowledge, there is no such theory. We did our squares and hexagons. We could have done it in two ways. One is by having, presumably, our equations do just what experiments do, and if we had a big simulation, probably we would have gone from squares to hexagons too. But that's not what we did. We had a small box, and the way we created our hexagons was in a using a box that had dimension square root of 3. This is square root of 3 times longer than this, and that is the equivalent of putting on a hexagonal grid in Fourier space. Whereas the squares we produced in a square box. Okay, so this is a good time to stop, I think. And let me check where I am in the class. I think the next topic is, this is just where I show more about those, if you want to see. This is the for instance, in the Faraday waves and hexagonal ones. This is instance in the velocity field. This is, and these are square patterns in a vibrated granular layer. I think I've shown these pictures before, and I mentioned in connection with convection, and I mentioned this remarkable fact that when I looked for pictures of square and hexagonal and other patterns in convection, I could not easily find them because their big time for experiments was pre-1990, hence pre-web, and things were not scanned all. I mean, I'm sure I could find them, I could take a look, but the things that you find on the web are, of course, things that date after 2000, when people were no longer doing elaborate experiments to see what they got in convection. They knew. So by then they were doing different things, like vibrating a granular layer, and there you get the same patterns. You get square patterns, these are square patterns. You get rolls. You get hexagons with defects. This is okay, and here you see the kind of difference between up and down hexagons, possibly. And there, these are, and this again shows the power of the theory. You know, you can go around saying you can say to people, oh, you got a hexagonal. How do you know? You don't know my equations. You don't have to know the equations. This is all math, it's all symmetry, it arises in any physical system that has symmetry. So I guess let's stop now and start again in about 15 minutes.